Okay, today we are going to study the first law for a control volume. We saw first law for a control system or a closed system. Today we are going to see the first law of thermodynamics for a control volume. This is something very important, especially for propulsion. Why is this very important for propulsion? Because most of the devices that we are going to study are steady flow devices. In your aircraft engines, starting from your diffuser, diffuser can be controlled, or it can be considered as a control volume, and you can do an analysis. Similarly, you can consider a compressor. You can consider a combustor to be a control volume, and you can apply first law. That is essentially you're applying the law of conservation of energy. And your turbine as well as nozzle. All of these devices are essentially control volumes. None of them are closed systems. They're essentially control volumes. So it's very important, or this is where we are going to apply the first law to kind of every device that we have when we are analyzing jet engines. Okay, whether it is ramjet or turbojet or turbofan, or if you're analyzing individual components, all these individual components are open systems or they are control volumes. Hence, this is the form of first law that we will actually be applying for the devices that we study. So it's very important that you understand it in and out, including the units and the terms involved, everything in and out. You have to be very clear with this particular equation. So let me just sketch a control volume. Like I told you, the box I am drawing is containing some of the device that we are analyzing. It could be a turbine, it could be a compressor, whatever. It could be any device, an open flow device, which is enclosed by this boundary, which is called the control surface. So this dotted surface is called the control surface, and whatever is inside this surface, this is called my control volume. Generally, the control volume is given by a V with a dash, just to avoid confusions, and the control surface, some kind of a stylish S you can put. So these are the two things. It's just like a black box. Okay. For my sake of analysis, I'm not interested in what is happening inside the control volume. It's just like a black box. I will not open it. How will I know what is happening is through what is happening on the control surface. I can measure something on the control surface, or I can get the variables that I want on the control surface. Using the information on the control surface, I'm trying to guess what is happening inside the control volume without actually opening and going into the control volume. This is the idea. Now let's assume that you have a flow that is, let's assume that we have a flow that's taking place into the control volume. Let's say this is the flow, this is the inlet to the control volume, and the properties at the inlet, you can say the velocity is C1, the temperature is T1, the enthalpy is H1, and if you take some datum, the height above the datum for the inlet is Z1. So you can say all the properties with a subscript of 1, or maybe I will use I. Okay, Ti, Hi, Ci, and Zi. And there is an outlet for this control surface from the control surface. So this is an outlet, and it is at a height of Z2 from the datum that we fixed. And the properties at the outlet are Ce. Okay, I'll use Ze, Ce, He, and so on. You can write Te, whatever properties are there. Similarly, over the control surface, you have a heat entering the control surface. Okay, because I'm going to consider a positive heat transfer. If there is a negative heat transfer also, then you can just take the net heat transfer. So I will consider a positive heat transfer into the control surface, and the system is doing some quantity of work on its surroundings. So the work done is also equal to W, right? So this is my setup. The box that I have, that's called the control surface. Everything inside the box is called the control volume. And without even knowing what is inside, it could be a compressor, it could be a turbine. I don't know. I don't want to open what is inside. Without even analyzing what is happening inside, just from the information on the control surface, that is at the inlet and at the outlet, I'll be able to say what kind of a device is it and what are the property changes and so on. So this is nothing but control volume analysis. And we are going to apply first law to a control volume. Okay, right. Before applying the first law, let's apply the law of conservation of mass. I think I'll go back to black color. Let's apply the conservation of mass principle. Let's say the mass flow rate at the inlet is m dot I and the mass flow rate at the exit is m dot E. Okay? These are the mass flow rates at the inlet and the exit. And the mass of the control volume, I'll write it as mcv. Okay. Now, if m dot I is greater than m dot E, consider the situation. What will happen to the control volume?
It will increase.
Yeah, the mass of the control volume will increase. What does it mean? It means, for example, if m dot I is equal to 3 kilogram per second and m dot E is equal to, it's just say 1.5 kilogram per second. That means every second 3 kilograms is entering the control volume, but only 1.5 kilograms is leaving the control surface. So you see that there is a stagnation. 1.5 kilogram every second is going to increase for the control volume. So you see that the rate at which the mass of the control volume increases will be equal to m dot I minus m dot E. Did you all understand? This equation is what I'm trying to explain. I was giving numbers to just make it simple. Okay, it's a very simple logic. Imagine if you have 3 kilogram per second entering and 1.5 kilogram per second leaving. Then what will happen to the mass of the control volume? You know that the mass of the control volume increases at the rate of 1.5 kilogram every second, and this is nothing but 3 minus 1.5. Okay, so if I subtract m dot I and m dot E, I'm going to get dmcv by dt. What is dmcv by dt? It is the rate at which the mass of the control volume is going to increase in time. Is this very clear to you? Any doubt? It's a very important equation. It's one of the pivotal equations. If you're writing, I'll just hold on for a minute. Then I'll go to the next slide. And I request you to pay attention. The theory is something very important. Don't just concentrate on solving the problems. You'll not be able to do any problem given to you. If you're strong in theory, any problem given to you, you'll be able to answer.
We have finished writing, sir.
Great. So now we are going to do a similar analysis for the energy of the control volume. Okay. So maybe I will, for a minute, I'll go back. Okay. Yeah. So what I'll do is I'll do a similar analysis for the energy. Excuse me. Again, I'll start with numbers. Yeah, I'll start with numbers again. Yeah. So let's imagine this is our control volume. What is the total energy entering the control volume? Say the energy entering is, let's say, 10 joule every second. Okay, or okay, we say 10 joule every second is the energy entering the control surface, and energy leaving or from the inlet, through the inlet pipe and through the outlet pipe, the energy leaving in the form of the fluid is going to be, let's say, 5 joules per second. And the system is given a heat transfer rate of, let's say, 100 joule per second. And the system is doing a work at a rate of 80 joule per second. Okay. Let's say these are the energy transfers given to you. Now, this 10 joule per second is carried by the fluid at the inlet. Please don't confuse it. So the fluid is also entering and leaving. It's not just heat and work. The fluid is also entering through the inlet pipe. It's leaving through the outlet pipe. So the fluid is carrying 10 joule per second of energy into the volume, and the heat that is entering the control volume is 100 joule per second. Whatever is leaving is the energy leaving through the fluid is 5 joule per second, and the energy leaving by work out of the control surface is 80 joule per second. So what is happening to the control volume? What's happening to the control volume?
Its internal energy is increasing 25 joules per
Yes,
second.
yes. The energy of the control volume is increasing, is changing. And if you find out what is the dECV by dt, the change in energy, it's going to be 10 plus 100 minus 5 minus 80. Okay, so because the energy entering is 10 and 100, the energy leaving is 5 and 80. So you see that the dECV by dt is equal to 25, like our friend has pointed out. 25 joule per second. So every second, the energy of the control volume is raising by 25 joules. Okay. So this is just using numbers. Now we are going to write using symbols. Now what is the energy entering? The energy entering is the specific energy is going to be E, which is or the rate at which energy entering is m dot into E. Sorry, m dot I into EI, which is equal to m dot into ui plus the kinetic energy term plus the potential energy term. So let me write it here. You have m dot into ei plus q dot. Okay, so q dot is the heat transfer rate and w dot is the work transfer rate to the control volume. This is equal to you just write it with black. So you have m dot into ei plus q dot is equal to m dot into e sub e plus oh, 1 minute. I think I have done balance assuming that control volume is steady. I'm going to do dECV by dt. The rate of change of energy of the control volume is the rate at which energy enters in terms of the fluid plus the rate at which heat is entering the control surface minus the rate at which heat is leaving through the fluid minus the rate at which work is done. Okay, and now this work I'm going to write it as W dot T. Okay, I'll tell you why. I'll tell you the reason a little bit later. So this work, the total work, including all the work on the control surface, I'll call it as W dot T. That's the net work done. Now let's simplify. dECV by dt is equal to m dot. What is EI? We saw energy is nothing but internal energy plus kinetic energy plus potential energy. So this will be GZI plus half CI square. This will be EI plus Q dot minus M dot UE plus GZE plus half CE square plus minus the W dot. I am going to split it into two parts. Okay, I am going to take all the work except for the flow work, because if you want a fluid to flow inside the inlet, you have to do something, right? You have to do something to push the fluid inside the control volume. So that work is called the flow work, to create the flow inside. And from fluid mechanics, you would have learned this as minus Pi into Vi, where Vi is the specific volume, plus the control surface is kind of pushing the fluid outside, so it's actually doing work on the surrounding. So this term will be a plus PE VE. Okay. Now why are we doing this? We are doing this because when there is an inlet, there is always a flow work associated with the inlet. That is, you have to push the fluid inside. The fluid will not automatically flow. So there is some work done in pushing the fluid into the control volume. This is kind of standard to every control volume problem. In any mass transfer happening, you have to push the fluid inside, and the control volume is pushing a fluid outside. So these works are always present in control volume problems. So we are going to take these works and put it with the energy term. Okay. So we're going to put this work in the energy term and this work in this energy term, right?
Sir,
Yes.
sir, for open systems, we won't consider the enthalpy, sir.
Yeah, we will consider the enthalpy. I'm telling you how enthalpy comes.
Okay, sir.
So far, is it clear?
Yes, sir.
This is like m dot I into EI, and this is like m dot E into EE. This is your Q dot, and this is your W dot T, the total work transfer. Okay. One small thing that we do is we are breaking the work. The total work on the control surface is being broken into parts. Okay, it's being broken into every work except the flow works. So all the other components of work, like for example, it can be shaft work, it can be displacement work. Any work other than flow work is put as W, and the flow work I'm going to separate. And because they are going to relate to the inlet and outlet, I'm going to add the flow work terms to the inlet and the outlet. Okay, so let me go to the next page. Now we will get dECV by dt is equal to m dot UI plus PI VI. Now I've added the flow work contribution here plus GZI plus half CI square m dot I minus m dot E UE plus PEVE plus GZE plus half CE square plus Q dot minus W dot. Now we see that in all the problems for control volume, you observe that internal energy along with flow work or the specific flow energy comes together. This combination is called the enthalpy, okay, HI. Similarly, UE plus PV. This combination we already defined it as enthalpy He. So this is the advantage, because there's always a flow. There is an inlet and outlet. There is always a flow work associated with the inlet and outlet. We are going to combine that with the internal energy, and we are going to call it as the enthalpy. So now we can simplify this equation as dECV by dt is equal to m dot I into Hi plus GZI plus half Ci square minus m dot E He plus GZE plus half Ce square plus Q dot minus W dot. Mind you, W dot is not the total work on the control surface. This is the total work minus the flow work. Okay, so it can contain any component of work. For example, shaft work or displacement work. Any work is okay except for the flow work, because we have just subtracted the flow work and put it in the mass flow terms. So this is the final equation that you're supposed to remember. So this is the energy equation, or the first law applied to a control volume. Okay. Right. I hope you are able to write down also.
Sir, shouldn't PIVI be negative because that's the flow work into the system?
Yes, it is in fact. It is in fact a negative. It's a negative work. Yeah. That's right.
So okay.
I have see if W is a positive work, then compared to that, PIVI is a negative work. Did you understand? Don't get confused with negative work, because this is a thermodynamic work. Okay, where I'm substituting for that, it is the thermodynamic work that I'm substituting in the energy equation. So PIVI is increasing the energy of the control volume, because you're pushing the fluid into the control volume. It will add to the energy, okay, because you're pumping the fluid in. You're spending some energy to pump fluid in. So that's actually going to give a positive contribution to the energy. But if you consider the work, or that as the work done by the control volume, then it will be a negative work, because you are doing it outside. Is that clear?
Okay, sir.
Most often, very often, this confusion with algebra comes into thermodynamics, because positive work and negative work, and the equation also contains some positive and negative signs. So this confusion comes, but if you slowly think about it, it will become clear. Okay, now let me go to this definition of what is meant by a steady control volume. Can you say what is meant by a steady control volume? What does the word steady relate to? I think you are doing aerodynamics in parallel, correct? So what is a steady flow? Can you repeat again? Okay, steady. Sorry, I did not hear. I heard some music. Steady means there is no change with respect to time. Okay, if there is no change with respect to time, then you call something as steady. So by steady control volume, in my analysis, I mean the mass of the control volume is not going to change in time, and the energy of the control volume is not going to change in time. So this is the definition of a steady control volume as far as the first law analysis is concerned. If you consider any steady volume, any control volume to be steady, that means the mass of that control volume is not changing in time. Okay, there's no mass accumulation into the control volume with time. Similarly, there is no energy accumulation into the control volume with time. So this is the definition of a steady control volume. Now this definition can be applied to your devices, right? For example, your diffuser could be operating in a steady condition. Your compressor could be operating in a steady condition. So this could be a valid assumption after a particular stage is reached, okay? But initially you may not, for example, if you take a diffuser, let's take a subsonic aircraft diffuser, okay? During starting, while you're just starting the diffuser, what is the mass flow rate at the exit? It's almost zero, right? You're just starting. So inlet, it is just starting to flow. M dot I is very small. There is a small mass flow, which is positive, and here it is almost zero. So during the starting, you see that the dmCV by dt is going to be not equal to zero. That is, the control volume mass will start increasing, and slowly you see that this mass will start going out, and once the m dot E starts to increase and it balances the m dot I, after some time you see that the mass of the control volume will not increase any further. So you would have attained a steady state. Okay, so you can make this assumption only after the device has reached a particular condition where the inlet and the outlet are all same and the mass of the control or the system is not increasing. But you should never apply this assumption during the starting of any device, okay, or shutdown of any device. While you're shutting down, you see that the inlet will be stopped, and still there will be some exit. Whatever is there, you have to blow it out. So the exit will be present. So the mass of the device will reduce. So during the starting of the device and during shutting down of the device, there will be a transient control volume. The mass will change. The energy will change. So you're not supposed to apply a steady assumption then. So where are you applying the steady assumption? Once the system has, started and it is going at a constant kind of a rate. Whatever is entering is now leaving. So there is, it's working at full swing, okay, probably at the design rate. Only at that condition you can apply a steady control volume. Is this clear? So it's not, again, same device can operate steady, can operate unsteady. When it is starting and when you're shutting the device, it will operate unsteady. It's called initial transient and your final transient. And only in the middle, your operation can be steady. So this is something that you should all know. Whenever you're applying the steady equation to any device, the assumption is the device is not starting or it is not stopping, but it has started for some time, it's operating, and now it has attained a steady condition. And after it attained a steady condition, you're applying this equation. Okay. So if we apply the steady control volume assumption, let me go back to the equations. dm by dt is equal to m dot I minus m dot E. Now this becomes 0. So my steady equations become m dot I is equal to m dot E. Right? And you know this very well. For a steady control volume, whatever mass is entering has to leave. If this is not happening, then the mass of the control volume will increase. Then it will become unsteady. So as for keeping this control volume steady, whatever mass is entering, it should be leaving at the same rate. Now coming to the energy equation, dECV by dt was written as m dot I hi plus gzi plus half ci square plus q dot minus m dot E he plus gze plus half ce square minus w dot. Now for a steady control volume, this is equal to 0 if the control volume is steady. So this means you can rearrange this equation as m dot I hi plus gzi plus half ci square plus q dot should be equal to m dot E he plus gze plus half ce square plus w dot. This equation is given a name. It is called the steady flow energy equation. Okay, because it's nothing but the energy equation. It's the first law of thermodynamics. But assuming that the control volume is a steady control volume and there is no energy change in the control volume. So the control volume remains at a constant energy with time. So whatever energy is entering the control volume, the same energy is leaving the control surface. Okay. Now, what is of prime importance here is, of course, this equation has to be memorized. You have to memorize equation 1 and equation 2. But something more important is you have to know the correct units. Okay. We have to know the correct units. What are the units that you will use generally? What is the unit of m dot?
kg per second.
Yes,
kg per
kilograms per second. What about h, the specific enthalpy? Specific enthalpy, what is the unit? SI unit?
per kg.
Yes, joule per kg. And what about g? We all know g is in meters per second square. It is the acceleration due to gravity. Z is the datum, so Z will be in meters, and C is the velocity of the fluid. This will be in meters per second. Okay, and Q and W, if these are in kilogram per second and the other ones are in joules per kilogram, your kilogram per second and joule per kilogram, the kilogram will cancel and you will get joule per second or watt. It's either watt or joule per second. Okay, the watt and work transfer are both represented by W, so I'm just writing watt so that you don't have confusion. And I'll clearly put Q dot and W dot for the heat transfer rate and the work transfer rate. Are the units clear? Please avoid using kilojoules. Can someone say what is the reason? Why should you not use kilojoule for enthalpy?
Not sure, sir.
Yeah, exactly. So because different terms are of different types. You see, especially if this is in kilo units, this is very hard to put in kilo units. At least here, instead of meter, you can put kilometer. If you use kilojoule per second, it will balance with a kilometer here. If you just put ZI in kilometer, it will balance. But if you want to make velocity into a kilo unit, it's not velocity directly, it's the kinetic energy. So it's very inconvenient. Okay, so to have a uniformity in the units, we always prefer base SI units. Never use kilo for the steady flow energy equation. Convert, if you have kilowatt, convert it into watt. If you have a kilojoule per kg, convert it into joule per kg. That way you will not miss in the exam. You have a calculator for the GATE exam allowed, so don't worry about the calculations. Always convert it into base units. So this is something very important. If you want to be successful applying the steady flow energy equation correctly, you have to be very careful with the units. Most often it is the units that will actually bring you down. Okay, right. So with that note, I'll go to the questions. Shall we do some questions? Maybe a quick revision. We started with what is meant by a control volume and why is it very important for propulsion, and we saw how to derive the mass equation for a control volume, and then how to derive the energy equation for a control volume. What is the meaning of the steady flow assumption or a steady control volume assumption, and what is the steady flow energy equation, the mass equation for steady control volume along with the units. Now we'll go to some problems very quickly. I would like to do a lot of problems maybe. Okay, first question is very simple, very trivial. Work it out, take your calculator, work it out and tell me answer. So let me write the details. P is 10 bar, 10 into 10 power 5 pascals. The temperature is 400 Kelvin. The velocity is 20 meters per second. The cross-sectional area of the pipe is 20 centimeters square. You should convert it into meter square. Okay. You're asked what is the mass flow rate of the pipe. Has anyone solved?
So is it 0.348?
Okay, one of you is giving the answer as 0.35. What about others?
Yes, sir, it's 0.35.
Yes. Yes. So the formula for mass flow rate, I hope you remember. This is rho AC, right? Density into area of cross section into velocity. Density you have to find, assuming that air is an ideal gas, P by RT, 10 into 10 power 5 by 287 into 400. For the GATE exam, I never do the simplification. I'll just put it here, 10 power 5 by 287 into 400 into area is 20 into 10 power minus 4 and velocity is 20. Now you can just feed that in your calculator and you will get 0.348. Sorry, yeah, 3484 something kilogram per second. Okay, and which can be rounded as 0.35. A very simple question. Why did I put this? Just so that all of us are on the same page. Now, how much is done in aerodynamics? I think Hero sir is also teaching aerodynamics in parallel, right? Have you done momentum equation for a control volume, mass momentum for a control volume?
Yes, sir.
Yes, sir.
Okay. Now, can someone just unmute and say, this equation has come after a lot of assumptions, right? What are the assumptions made? You would have learned this in fluid mechanics or aerodynamics.
It's a steady.
No, this has nothing to do with the control volume. It has to do only with the control surface. That is, you have a control surface, and in some portion of the control surface, there's an inlet or an outlet. Okay, let's say there is an outlet like this. Now, what is the rate at which fluid is escaping, or what is the rate at which fluid is entering if it is an inlet? So you would have done something like this, right? What are the assumptions made to derive this equation?
It's a steady flow.
No, steady is not an assumption. Oh, steady in the sense you're okay. The velocity is not a function of time. Okay,
Yes.
that way it is a steady velocity. Okay, let's say a steady properties over the control surface. Okay, accepted. Any other?
Law of conservation of mass.
No, this is not. This has nothing to do with the conservation of mass. Okay, don't get confused. This is not mass conservation. This is the flux of mass through a surface. Shall I tell you the assumptions so that you can remember it or you'll get reminded? Yeah.
The flow is considered to be incompressible.
Not necessary. Not necessary. This is even for a compressible flow, it will work.
So the area vector is constant.
Area vector is constant.
That is, it's for a plane surface.
It need not be for a plane
like
surface.
so I mean to say that the control volume which we are taking, so the control volume should have a plane surface in which the
Okay.
fluid is entering.
Okay. Right. Agreed. Okay. It is like a plane kind of a control surface. It has no curvature, let's say.
Yes.
Yeah.
Sir, we will consider line integral.
Yeah, it's a surface integral. It's a surface integral.
Okay, sir.
So also the flow velocity is constant throughout the cross section.
Yes, the word for that is uniform. Okay.
Yes, sir. Uniform across the cross section.
So integrate.
So
Yes.
also the density is constant. The density is uniform across the
Yeah.
cross section.
I'll include it in velocity. Velocity and density, they are both constant, uniform. The last one is the
So,
velocity
and
is. Yeah.
I think the volume that's entering is same as the volume that's leaving. So there's no accumulation or any other losses in the middle.
No. This equation has nothing to do with mass conservation. Okay. This is just the mass flow rate through a surface. It has nothing to do with the volume. Okay. You just have a surface, and what is the mass crossing that surface? Okay. Conservation has inlet and outlet, right? A volume will have inlet and
Yes,
outlet.
sir.
This is just for a surface. What is the mass entering or going through a surface? Now the second or the last assumption is the velocity is normal to the area. Okay. Otherwise there will be a cos theta component present, right? So go back to your aerodynamics. Unless these assumptions are put, you will not be able to arrive at this equation. And the general equation that you would have learned in aerodynamics is this is a surface integral over whichever part of the surface, rho v, or let me put c dot n ds. Okay. If you go to your fluid mechanics, then you would have learned the mass flow rate through a surface. It can be any portion, any bit of a surface. You can even take a random surface like this and consider a normal to the surface to be here, and then the velocity of the fluid to be like this. Then rho is the density over the control surface, and the velocity can also be changing. Okay, it can change from different point to point. Density can change. If changes, or the most general equation is this. This is the most general equation. Out of this, if I pull rho out of the surface integral, rho has to be uniform on the surface. So I'm pulling a rho outside. Then if I pull a c dot n outside, then c dot n should also be uniform. So c and there's no c dot n term, there's just c term. C dot n will have a c cos theta. So the cos theta is not present because I'm assuming c and n are both along the same direction. That is, the velocity is normal to the surface. So after making a lot of assumption or all those assumptions, you end up getting this equation. Okay. So if you do not understand this very well, then it means you have to go to your fluid mechanics. I would suggest Fluid Mechanics by F.M. White or any equivalent book. It will contain expressions like this, and you can go and kind of read this in detail. Control volume analysis is something very important for aerospace engineers. So if you don't understand what I'm trying to say here, you have to go to your fluid mechanics. But it will not affect much in propulsion. Okay, it's not going to affect our propulsion that much. So henceforth, I'm going to move on. Okay, now this is the second question today. Can we do this quickly? Again, it's taken from a GATE paper. Try to work out this question and then give me the answer.
Reginald sir, am I audible?
Yeah, I'm audible.
Okay, sure. Thank you, sir. Thank you.
Any problem?
No. I thought is there any technical issue that I can help? I think it's
No,
going
no,
good.
no.
Sorry, sir.
Yeah,
Yeah.
I was waiting for the students to give an answer.
Great. Please go ahead. Thank you. Yeah.
Has anyone solved it? Um, it's taking a lot of time. Do you need some help in between? Guys, where have you reached? Maybe I'll ask questions. What is the mass flow rate?
7.09.
Very good. That's a check. 7.09 kilogram per second. It's a check that you're going right.
Got option A.
Okay,
Yes, sir. The mass flow rate is 7.09 kgs per second.
great. So one of you has given me the answer as 156.4 degrees Celsius. Now let me explain the answer very quickly. I'll tell you what is the catch here. Okay, it's something very similar to your gas turbine engine, right? You have a compressor, then you have a combustion chamber, and then followed by a turbine, right? A simple turbojet engine will have something like this, except for a heater, you have a combustor. So the catch here is you're given the volume flow rate instead of the mass flow rate. So if you take continuity equation as the volume flow rates are equal, you're going to make a mistake because you're going to assume an incompressible flow. So if you think you get 2.33 meter cube per second here, it is wrong. Okay. If you proceed it that way, you'll not get the answer correct. This information is given and the temperature and pressure are given here. So at this section, you have to find what is the mass flow rate using this information. Because mass flow rate is not going to change. Mass conservation will always hold true. Volume conservation will not hold true unless it is an incompressible flow. So mass conservation holds true, which means you have to first find the mass flow rate. The density is nothing but P by RT, which is 276 10 power 3 divided by 287 into the temperature is 43 plus 273 Kelvin. If you do this, you get something like 3. I'm getting 3.043 kilogram per meter cube. This is the density at the exit of the compressor. At the compressor exit. You know the volume flow rate at the compressor exit. So I can find the mass flow rate at the compressor exit as 3.043 into the volume flow rate 2.33. This will be 7.09. Your kilogram per meter cube into meter cube per second will make it kilogram per second. So this will be 7.09 kilogram per second. Once you figured out the mass flow rate at this cross section, it is 7.09. The same mass flow rate should be present here, 7.09 kilogram per second. Now you apply the steady flow energy equation to the turbine. So you apply the steady flow energy equation to only the turbine. In that case, you get m dot I hi, and I'm going to neglect the kinetic and the potential energy terms, because assuming that it's horizontal and the velocities are not given, so you can assume that they are same before and after the turbine. You can write m dot I hi plus q dot equals m dot E he plus w dot. And if I rearrange or if I replace m dot E, m dot I and m dot E are same, so I'm just going to use m dot he minus hi is equal to q dot minus w dot. Okay, I'm keeping the enthalpies on one side and the heat and work on the other side, because I have to find the air temperature at the exit. So I'll keep the exit enthalpy on the left side. Now if you write this as m dot, because air can be assumed as an ideal gas and you're also given the Cp value and gamma values, you can write he minus hi as Cp Te minus Ti equals q dot minus w dot. Or on rearranging, you can write Te equals Ti plus q dot minus w dot divided by m dot into Cp. Okay, I've not simplified. Now I'll put the values. Ti is 430 degrees Celsius. Because it's a temperature change, I can even put it in Celsius. It will not hurt. Q dot, you're given that heat is lost from the turbine to the surrounding. So Q dot is minus 90. And W dot, because the turbine produces 1860 kilowatt, it's going to be a positive work transfer. So this will be a minus 1860 kilowatt. And I have to be careful converting them into kilojoules, or I'll substitute Cp in kilojoules. So this will be 10 power 3. M dot is 7.09 into 1005. Let me just work it out. Yeah, so this makes it 156.33 degrees Celsius. Okay. So the answer closest is 156.4. Okay, what are the possible sources of error? What kind of error could we make? I have seen my students making these errors. If you did not make the errors, well and good. If you're making these errors, try to avoid them consciously. One is they may assume that the same volume flow rate is present here. That's a conceptual error, because you're treating the fluid to be incompressible. It need not be incompressible, because it is air, first of all, and the velocities may not be small. Okay, they may be large enough that the fluid is actually not going to be incompressible. So do not make this assumption unnecessarily when it comes to thermodynamics. We are very used to making this in fluid mechanics, that the flow is incompressible. But when it comes to thermodynamics, especially when you're working with ideal gases and you're working with flows like turbines and compressors and nozzles, you should never make this assumption on incompressible unnecessarily. Okay, only when it is required you can make the assumption. Here clearly it will not be incompressible. So you have to find the mass flow rate from the given data. And then mass flow rate, mass conservation is actually going to hold for both incompressible as well as compressible flow. Volume conservation is only a concept for incompressible flow. So now you find what is the mass flow entering the turbine. You know the same mass flow is going to leave the turbine, because we are going to assume that the turbine is operating under steady flow conditions. And now when you apply the SFEE to the turbine, you're able to find what is the exit temperature T. And another mistake that commonly happens is your signs for Q and W. Your Q dot and W dot, if you do not put the correct sign, then you can make mistake. I've seen students doing that. And also, if you do not consider the kilowatt, if you don't convert the kilowatt, then also you'll get a very weird answer. You may not get the correct answer. Okay. I hope this is clear. Any doubt on this?
So if the same problem compressor inlet is given, we can make work done on turbine is equal to work done on compressor.
If you are given that the turbine is running the compressor, okay. Again, if that you cannot always take that assumption to be true, because the turbine could be running something else also. But if you know that the turbine is running the compressor, that information is given, then yes, you have to use the information that turbine is running the compressor. That's a good question. In fact, for your gas turbine cycle, your Brayton cycle that we will analyze, we are going to assume that the turbine is going to run the compressor. A portion of the turbine work goes for the compressor. We are going to make that assumption when we do cycle analysis. And when it comes to jet engines, that will be a major assumption for us. In fact, for the jet engine, it's not like the land-based gas turbine engine, which is required to produce work. For a jet engine, you want kinetic energy. So the main device is you want to expand the hot gases in a nozzle. So the turbine is sitting only to drive a compressor for a jet engine. But in a land-based gas turbine engine, the compressor work will only be a small part. Majority of the turbine work will go for running the generator. So depending on the situation given, you should be able to make the decision. Does that clarify?
Yeah, okay.
Okay, great. Right.
So also one more thing.
Yes.
So while we are applying the steady flow energy equation for the turbine, so we are assuming that then there is no change in velocity.
Okay.
So is there actually in the real case, is there no change in velocity across?
A good question. A good question. But I cannot give you the answer immediately. In fact, I'll make a note of this question, and we will come back when. Yeah, I'll make a note of your question. Okay. So the assumption that we
also we do not change. We do not take the change in velocity.
Correct. Correct. Right. So let me write that. Let me forget compressor for a moment, but the same explanation will be true for compressor or turbine. So if you take a turbine, the inlet velocity is Ci and the exit velocity is Ce. The most common assumption that is made is the delta kinetic energy through the turbine, which is half Ce square per unit mass flow minus Ci square is negligible. Okay, and your delta potential energy per unit mass, which is G into Ze minus Zi, is also neglected for a turbine. Okay.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.